A small can is hanging from the ceiling at height h above the ground. A small ball is aimed directly at the can, as the figure shows. At the instant the ball is fired, the can is released. Ignoring air resistance, show that the ball will always strike the can, regardless of the initial speed of the ball. Assume that the ball travels a horizontal distance of r before the can reaches the ground. So, let's start by calculating the time it takes for the ball to get across the horizontal distance r. So to do that, we can start by breaking up this vector, the velocity vector VO, into its components using vector decomposition. So if this is the launch angle, theta, this would become the initial velocity times the cosine of theta, and this component will become the initial velocity times sine of theta. And these two, the cosine is the horizontal component of the initial velocity, and the sine of the initial velocity times sine of theta is the vertical component of the initial velocity. So, to find the time it takes, we can use this equation here. It says that the displacement is equal to the initial velocity times the time interval, plus 1/2 times the acceleration times the time interval squared. But since there is no acceleration in the x direction, there's no acceleration at all in the x direction, so this whole part can get omitted. So, and the displacement or change in x is simply r, or the distance, the horizontal distance r, as shown in the diagram. So we can say that r is equal to the initial velocity in the x direction times the time interval. So that means that the time interval is equal to r divided by the initial velocity times the cosine of theta. Because if you remember, the initial velocity in the x direction is the initial velocity times the cosine of theta. So I should probably label that as well. Y. So that is going to be important, as we are going to use that later. So from this, we can say that the change in y of the ball is going to be equal to the initial y velocity times the time interval minus 1/2 at squared. Again, this is from this kinematic equation here, up here, except we're applying it in the y direction. So this will become g instead, and this will be negative since it is pulling it down. It is accelerating the ball back down to the ground. Gt squared. Since the acceleration is g, I'm going to replace it with that. And that gives us the equation for that, for the y position of the ball. So to get its position at any time instant, we can substitute that with the y of the ball minus the initial y position of the ball. That is equal to the initial velocity in the y direction, which is the initial velocity times the sine of theta, sine theta times the time interval, minus 1/2 gt squared. And now, the initial y position of the ball is going to be 0 meters above the ground, because it in our reference system, the origin is where the ball starts. So when the ball starts, its x position is 0 and its y position is also 0. So this part is 0 and can be omitted. So from that, we get that the y position of the ball is simply the initial velocity times the sine of theta times the time minus 1/2 gt squared. And we're going to substitute everything for the time later, but I'm just not going to substitute it yet. So, and you'll see why in a second. There's that. That makes some room. Again, we figured out time is equal to r over the initial velocity cosine theta, and that the y position of the ball is equal to the initial velocity times sine theta times time minus 1/2 gt squared. And that's everything we have right now. Now we need to figure out the y position of the can. So the change in y position of the can, again, we can use this kinematic equation again, is equal to the initial velocity of the can, which the initial velocity of the can is simply 0 meters per second because it is simply released. The can is simply just released, meaning it's not thrown down, so it has no initial velocity. So it is simply equal to minus 1/2 gt squared, as that is the acceleration that is pulling the can down towards the ground. Now we can replace this again with the position of the can at any given moment minus the initial position of the can. That is equal to minus 1/2 gt squared. The initial position of the can is h. It starts at a height h above the ground. So the position of the can minus the height is equal to minus 1/2 gt squared. And that is at any given moment. So solving for the position of the can at any given moment, find that it is equal to h minus 1/2 gt squared. And that is going to become important in a moment. So the y position of the can is given by the height minus 1/2 gt squared. Now to figure out whether the ball will hit or not, we have to figure out whether yb is equal to yc at any given moment. To do that, we have to say that the change in y between them, which is simply yb minus yc, it's the difference in their y positions at any given moment. That must equal 0 for them to hit each other. But we don't know that yet, so we need to prove that it's going to equal 0 at any given moment. So I'm going to write this down. And now all we need to do is substitute everything from these two functions. This is equal to initial velocity sine theta t. I'm not going to substitute t yet, and I'm going to show you why. Minus h minus 1/2 gt squared. Now if you look at these, you'll immediately notice that after distributing this negative, this will become positive. So these two 1/2 gt squares will cancel each other out. So what we're left with is simply the initial velocity times sine theta times the time minus h, and that is the difference in y between them. So this is why I didn't plug in t yet. This is to keep it simple, so that you don't have to write as much and do as much work. So I'm going to rewrite that. We had sine theta t minus h. That is equal to the y difference between the two of them. So now we can replace everything with t, which was the distance r divided by the initial x component, x velocity of the ball, which is VO, or the initial velocity times the cosine of theta. So now we can replace that. VO sine theta times the time r divided by initial velocity cosine theta. And we're going to subtract h from all of that. So if you notice, multiplying this, the initial velocities will cancel. So you're left with change in y equals to r times sine theta divided by cosine theta minus h. And now sine theta minus cosine theta, or sine theta divided by cosine theta is tan theta. So the y difference is simply the distance r times the tangent of theta minus h. And now, if we look back closely at the diagram, we'll see that the tangent of theta this theta angle here is simply the opposite divided by the adjacent, opposite over adjacent. So that is going to be the height divided by the distance r. So by manipulating this, we get that r tan theta is actually equal to the height. So meaning that this we can substitute as h minus h, which is simply 0. So that means that the y difference between the ball and the can at any given moment. So let's say if we fire the ball and the ball's here, and we drop the can will be at the exact same y level at any given moment. So the initial velocity of the ball doesn't matter as long as it can travel the distance r before the can actually hits the ground and everything stops. So this is how you would prove that the ball will always hit the can if there's no air resistance and if it reaches the can in time.